Okay, so just where is my pen? Yeah, perfect. Okay, so today we're gonna start something known as clustering algorithm here. Now, before going to this algorithm, let's create the premise first. So far we studied the algorithms which are supervised in nature, in which we wanted to predict something. Uh, that could be maybe you were predicting salaries, basically the thing which is continuous in nature, or we were predicting something known as class. So whether spam or not spam. Now these are known as supervised. You already know in which. Yeah, just a moment. Need to change the pointer in color black. Still pointer is not visible to me. Just a minute. Okay. Anyway, so we were right. Okay. So in supervised, we all know that we were given the data and then we have label. So any problem in which you are solving, you are trying to build or fit your model onto data to get the label, which is your predictions. This is supervised. But now we are entering into something which is known as unsupervised algorithms. As name suggests, these algorithms are unsupervised, which means that you won't be providing any label. So there would be no label. It's just that you would be having data, you would be getting data, and then your tasks would be vary in the form that you need to come up with some sort of relation clusters with the data provided to you. So these algorithms are known as clustering algorithms because eventually you want to bring some clusters or group your data into some different clusters, so to say. And this is one kind of a unsupervised learning because here you would be just dealing with the data. So the motivations that by clustering here. So initially the first thing is the customer segmentation case. Okay. Okay, so customer segmentation here. So initially, suppose you are working for a company which are into some e-commerce or retail banking. Your task is to group your customers. So basically, the data which you would be having is their spending habit. You would be getting the data of their purchases done in the past, the amount of purchase being done, how many times did they make the purchase, what was the item. So basically, all the spending habit of yours, and then what is your frequencies, product preferences, which area you were focusing more. And then they wanted to basically divide categorize you into a kind of a high spender, occasional buyer, and discount seeker. So these are three names, and while doing so they wanted to target their market campaign. For example, the guy who are already kind of uh, already on a permanent, or so to say the believer of the e-commerce, some say Flipkart. So that guy won't be shifting to Amazon for some discount maybe. So these guys are good. So but there are some guy who might be switching from Flipkart to Amazon, generally how we do. So these are the one where I wanted to target my market campaign. I wanted to give more discounts, right? So therefore they wanted to segregate their customers into different segments based on the past data of all the people, all the colleagues. For example, you got data of thousands of customers in the past. Now a new customer coming up into the picture, new sign up happens to a Flipkart or Amazon. Initially that's a cold start. I mean, you do not have any pattern of that guy, but based on his maybe the age, the demography, etc. You could initially put him into one category. So this is what a customer segmentation. That's how we do that. That's why we do that. Second case is the anomaly and fraud detection. You are getting the data of different cases, different transactions happening. So a fair transactions forms a one kind of cluster having a specific behavior, but suddenly an anomaly occurred there, an abnormal behavior. Then the characteristic of that abnormal behavior would be different from the transactions which were done under the normal category. So we also want to deal this thing. Now you might be think that why not this problem can be solved with the supervised. So of course, this problem can be solved by the supervised. For that, you would be having data and label. So if somebody provided you data and label, your problem would be solved. Now, can anybody tell that still we got the data and we got the label? Why going with a supervised would be can be a little challenging or tricky? So just any pointer if somebody have in this direction. So we are provided with data. The same problem we are having the label normal, abnormal transactions.
There are too many labels that we need to provide, and that could be tedious maybe.
Too many. So labels would be only two things. The transaction is normal or the transaction is abnormal. So maybe can you think in this direction?
Sorry, can you repeat?
So label would be only two things. Either the transaction is normal or the transaction is abnormal. So you would be having the data and such labels, and we can solve this problem by a supervised learning, like logical regression, random forest decision trees. But still, these problems are well suited for the unsupervised learning. So can you think some idea why unsupervised is a better option in this scenario?
So one thing what I can think of is
Hmm.
so one thing what I can think of is when we have a supervised in advance, like we classify in normal and abnormal, we give the data label. So and when we have this kind of different behaviors,
Hmm.
so still there is a chance that we can mix the normal and abnormal in both the categories. So because we are already deciding that there
Yeah.
is a
Yeah, partially agree with that. So a few of the characteristics might be shared between the guy for the transaction which is normal or abnormal, but major challenges comes from the point that the this in this data generally such data, the chances of the abnormal transactions are roughly on the margin of say 1 out of 1 lakh. You will or for considering a lot of transactions happening on the e-commerce sites, millions of people buying things or doing coming to the site of Amazon, Flipkart throughout the world. So even if you prepare this data, the abnormal transactions would be lesser and normal transactions would be huge. So if you try to model this data, so chances are that even your model gonna be more biased towards the normal scenarios because model doesn't see that many abnormal futures so that it can fit well on the abnormal cases. So for that thing, what you can do, what you might be doing that, okay, now I got say 5,000 normal scenario. I got 10 abnormal scenario. So I might, make this data duplicate 50 times. So 500 such data of this type. So basically you duplicate or multiply your data or make it large with the similar characteristics. Still, what will happen? Your model would be trained towards toward the characteristics of these 10 abnormal classes. So any abnormal case which appear up, which is basically kind of not this scenario, but still that's a abnormal. Your model will say that that's a normal case. But however, that's another kind of anomaly which never seen in this abnormal cases. Reason being, we do in general scenarios we do not see abnormal cases a lot. Uh, Therefore, fitting a model on such scenarios is not that promising. Will not make your model that much trained on the abnormal cases. So chances are that your model still doesn't perform well. That's why not go into the category that train your model or make your model understand only the normal data. Let model understand that this is how normal data looks like. And if something comes out of out of the purview of this normal data, that's an abnormality. So here you understand that, right? We do not need any label. I'm just creating a model which basically try to understand how a normal data looks like. Now anything which doesn't resembles the characteristics of a normal data, that's the abnormal. That's the abnormality. So therefore unsupervised is a kind of a good algorithm here. Here you will try to understand the normal data, you cluster them, and any point, any data set which doesn't lie into that, that's the abnormality, right? Therefore it is preferred that that unsupervised learning clustering algorithm could be one of the kind of a better way of doing that. However, having said, if somehow you come up with the case that you have a decent abnormalities cases in your data, then it's okay. I mean, then in this case, supervised algorithm will also work well. So premise is that it's not the case that you apply unsupervised, supervised will not work. Both will work. We have to find that which works better in in this scenario. So as of now, considering that abnormalities being found less in the universe, uh, supervised algorithms or unsupervised or clustering is a good to go. So this is some example. Now take one more example here, image segmentation. Nowadays, these things can be done with deep learning and computer vision. But initially, if I gave you the images and I asked you to image segment the images, for example, these things would be segmented. The blue sky would be segmented. The clouds would be the green patches would be segmented. The lake would be segmented, so on and so forth. So you need to basically group them. So all such pixels becomes one group, group one. All such pixels becomes group two, group three. This becomes group four, and this whole again group one. So basically, and this is group five, the brown part. So basically, roughly this picture contains five group. So here the idea is that uh, the input gonna be the pixel, basically images. On when we say images, it is RGB pixels, and then we have to model cluster them into that many group that all the groups become separate. So this is one kind of clustering, image segmentation. But nowadays uh, the computer vision, the advanced computer vision, deep learning can do it very easily. But again, this problem can also be used to be solved with the help of image segmentation, because in general you are just doing nothing but making the groups of the pixels which belong to one category. So green pixels belong to landscape, clouds, cloud bluish part, lake, and so on and so forth, right? Okay, so now I think the idea is pretty much very intuitive of clustering. Why we do our clustering? Because we want to segregate our data into different mutually exclusive set of groups. So basically, uh, just a moment. Is there any other option? And okay, now so finally thing promises that they have one group, group one, group two, group three, group four. Suppose we group make our data into different groups. So this group will have all the data points, all the person, customer, say transactions who lies in this group. They share same characteristic, very closely sharing the same characteristic. The guy who are into this group closely sharing the same characteristic. However, the characteristic of this group would be very different from these groups. So that's the idea, to br- group your data into different clusters. So now cluster means cluster is same as group. Partition, you can say anything, right? This is the objective of of doing the clustering. So now try to understand, before going into how this algorithm works, let's try to understand something. So eventually the goal of clustering is what we mentioned: group data point, data close or similar to each other, understand, identify such grouping in an unsupervised manner, of course, just working on the data. That's what we kept. Now how to define similarity? Because eventually you this is the data. For example, the data would be in the column 1, column 2, column 3, column 4. It would be price something. So the data is gonna be just numerical, categorical, the data the way you have seen earlier. Now how you can define the similarities between the rows, that row 1 is similar to row 5, row 5 is similar to row 10. So how you can bring the similarity, that notion we want to understand. And finally, up to how many times shall we keep doing this activity, of basically the whole algorithm, so that we can say, okay, this is the perfect number of clusters. So we're gonna understand this thing. So here these guys are one cluster, these are second cluster, these are second cluster, these are second cluster, right? So there could be the cases that you might ask that even this could be the cluster or this could be the cluster. So how this guy being decided to come into this cluster. So this we're gonna see that this guy has more closure to these people as compared to the these people, this guy. So this is how algorithm works. We're gonna see that. Okay. So before going to the cluster, just one term we need to understand in this algorithm. It's kind of very intuitive or very easy algorithm. Centroid.
Raj, sorry. I think I
Yeah, yeah.
missed one point. Uh,
Hmm?
did you say when we define it, do we define the number of clusters, or how do we know
Yeah.
how
Hmm.
many?
We're
So
gonna come to that. So your
okay,
question is how we gonna define that they're gonna 4 cluster, 5 cluster, right?
yeah,
So
exactly.
this we gonna come up. So that's a good point because eventually you would be working on data row number row 2 to row say 10,000 or 1 lakh. So you by just looking at the data which is just numerical or categorical, you want to be able to you able to figure out that should I go with 4, 5, 3. So that we're gonna do that. Okay. So let's understand the term centroid. Centroid is nothing but a single point, the single point of each group, which is a mean of these points. So these 3 points, the mean of that would be a centroid. So mean of this cluster is known as centroid. So centroid is computed as the mean of all data points in the cluster. So in Sabka, in this one, they are like with 10, 20 points. The mean of all the points would come up somewhere here. So that's the centroid. So this is a one understanding which we need to keep in the mind right now. So let's go ahead. So now we will try to understand the very first algorithm, which is known as k-means algorithm. So before understanding k-means algorithms, in general, our clustering algorithms are divided into, not divided, the types of clustering algorithms are k-means, that first algorithm. Second is agglomerative clustering. There is one more, but we're gonna discuss these two. K-means and agglomerative clustering. This one is also known as hierarchical clustering, but we will come up one by one. So we will understand k-means. So here k denotes number of clusters. So this algorithm says that k-means clustering. We are going to cluster our data into two groups. If I say k equals to 2, then I'm gonna make the 2 clusters only. The logic I would be applying would be means, so which we have understood the centroid thing, means of all data point. This is how a general k-means names suffice. So now let's first I'll tell you the algorithm how k-means works. So, and then we will come up how to choose the k. So first thing first, let's suppose in this data, because it would be easier to do all the mathematics, I assume k equals to 2. So initially I assume that I I am going to divide all the green points into 2 data. So what you will do in this out of this 2 data, you will choose k random points as clusters. So suppose all the where the green points are here. This is some kind of green point. This is some kind of green points here, and you choose any 2 points. Any 2 points you choose out of these data points. So suppose one of my point came out to be here. So this is one of the point. The one point could be this one also. The second point could be this guy also. But just to understand the algorithm, the chosen points, the very first step of this algorithm, step 1, choose any 2 data point. I choose this point and then this point, right? Next step, assign data points to the closest cluster. So what I'll do, all these many points, I will find the distance of this point from this point. Suppose this point, the distance of this point with this is d1, and the distance of this with this point is d2. So we will write, and this is suppose point 1. So point 1, d1 distance, d2 distance. This is suppose 0.25, and this is suppose 0.50. So we will see, okay, P1 is closer to this cluster 1, cluster 2. So allocated cluster would be C1. Simple. the point which is closer to the cluster, that cluster would be assigned to that. So C1 is assigned, P1 is assigned to C1. Now second point, P2. P2 is, suppose this guy is P2. So same distance, calculate the distance from this and this, this and this. Finally, C2 is the closer one. So this we're gonna do for all the points, right? So what happened? Roughly, these points are the one which are assigned the cluster C1, blue one. These are the points which are assigned the cluster C2. So I think this part is clear. C2, these all red guys are this one assigned to this C2, and all blue guys are assigned to this guy C1. After doing this step, what we're gonna do? We're gonna calculate centroid. A centroid is what? Centroid of blue point would be mean of all the blue points. Simple mean. So what happened after doing that? This centroid will move. Suppose after the once we find the calculate the centroid would come up somewhere here. So this guy will come the new centroid X, and the centroid of red guy will become the updated centroid. Suppose here this guy. So now this is what happened. This is the updated centroid. Same process will happen. We will calculate all the distances. So what will happen now? These guys are assigned this cluster, and these guys are assigned this cluster. And then what will happen? We will update again we will find the centroid of the updated point, and we will change the centroid. And eventually what happened? We will keep doing this step until unless no point swap. Finally, the no point swap means no blue point becomes red, no red point becomes blue, and we will stop the flow. And finally, the centroids would be updated, and these points becomes one cluster, and these points become cluster 2. So you understand how the step. So I'll start once again. Choose any two random points here. Any random points. You can choose this one. Eventually, it would converge. All the points closer to x1, x would be assigned this cluster. So these points become cluster C1, just to name, and these guys becomes assigned cluster C2. After doing so, you will take the centroid of C1. That becomes your updated cluster centroid. So updated centroid will move from here to here. And similarly, this red guy, after taking the mean, will shift to somewhere here. Now we will repeat the same process. Calculate the distance of all the points with the updated center, and assign the cluster to the point which is closer. So these points are now closer to this blue centroid, and these blue guys are closer to this red centroid. Then they becomes red, and these guys will become blue. They become blue. Update the centroid. How? Taking the mean of all the points. So this centroid will now shift to here. Shifted to here, and this guy shifted to here. And finally, again, calculate the distance with the updated centroid and see which points moved. At this point, no point moved. I mean, all the points which are blue, it's closer to blue centroid, and all the points red are closer to the red centered. So we stop the convergence because now no point is shifting. So no need to update centroid. Once this is done, what you do, you bring all the rows of same characteristic into one centroid. Towards one centroid, basically one cluster, and here it becomes a second cluster, right? So finally, this is the end. So any doubt in this? Pretty much very neat, smooth.
So Raj,
Yes,
what I understood is centroid is like the center of gravity. I'm just imagining. So where the heavier mass or heavier particles are there.
Yeah,
So
center of point. Yeah.
so it means that, but again, it is average only, right? So it is in this data sets which are distributed, it is the average of all the points, and then we are taking the distance from the average of all the points, and then again we are repeating it until all the parts are, or all the points are classified or segmented.
Yeah, pretty much that much, because if you mention the word center of gravity, so all the points which are closer to the center, they forms one cohesiveness. They are more closer to each other. So that's the idea, is that always assign the point to the nearest center of gravity, so to say, if you want, or center of mean or centroid, and then update the point, update the centroid. So basically you are assigning the centers, assigning the point to the center, and then you are updating the centroid so that your center of gravity moves to the right point. So that's how we're doing. Eventually what happen, this is somewhere we will end up, because now all the points are segregated. So you the mass of these points somewhere here, and these points are here. If
Yeah,
this point would have been, this point would have been closer to here, this point would have moved in this side, and we would have calculated the centroid. But here now that point is not necessary. So the algorithm, that's how we converge this algorithm. So point is, do till convergence. I mean, the step is that choose k centroids, say k points, any k rows as center, calculate distance of all points with center, assign assign centroid either C1 or C2 2 points based on distance, lower the better. Fourth, update centroid by taking mean of all points. Once this is done, same, repeat this process, so that finally we would add from here, then here, then again moving the centroid to the better shape. Now again, of course, practically, if you see, these points are close, these points belongs to this cluster, because this is pretty much visible in 2D. So therefore these points assigned to this, update the cluster is updated. Now we are almost ending up with some borderline cases here, same the process, and then this is that. Finally, this is how our clusters segmentation happened, and this is done. So this is k-means. Here you decided that I am gonna go with the k equals to 2 cluster. Now problem with this algorithm is that even if you would have chosen here 3 points, even if you provided here 3 points, and this then having 3 centroids, maybe third centroid somewhere here, centroid 3, centroid 2, centroid 1, the model would have divided into 3 centers. So maybe this part somewhere belongs to this part is almost closer to this somewhere. So now point is that this is pretty much wrong. I mean, here it just practically 2 centroid neatly practically visible to us. But if you say that no, I'm gonna go with k equals to 3, so that's a kind of wrong assumption. Now point lies in the question, the very first question you asked, that how to find the optimal number of k. So this is one kind of activity which always happens before applying the k-means. So that we're gonna see. So I think algorithm is pretty much clear. Some mathematics every time. So iteration means first run. When you calculate the distances, you calculate the distance of all the points with centers n points. So the work you done is k into n, and then you calculate the mean of each time. So this, which is on. So this is the computation. So this algorithm is very fast, because it just happens. The change in the cluster is on, and this is almost okn. K is very small, 1 2 3 4, so even it is lesser than or big O of n square. I mean, so just the idea is this algorithm is very fast. Now pros and cons here. Simple, fast to compute, understand. convergence to local minimum within cluster squared. Okay, but cons. Very first con, setting k. How to decide that what is the optimal number of k? That is the thing which we have to deal with. Sensitive to initial centers. What if I forgot to remove the outliers somewhere here. I forgot to remove the outlier. All the mean would shift toward the center, very far away from in the initial cases, the ideal clusters was supposed to be here. These guys, and this guy should have been removed from the picture. But just because we forgot to remove the outlier, so the initial mean points becomes here and here because this number is huge. So therefore, you know that our clusters is now pretty much bad now these case. So this is the undesirable effect of having sensitivity to initial centers, outliers. Sometime in this scenario, I my actual now this is something which is into the area of astronomy. In astronomy, we see different kind of star systems. Somewhat here. So this is, or we see various galaxies, their shapes. So if you apply k-means on this data, it's very difficult because here I wanted to shape, make my cluster in this way. This is the optimal clusters, but just because the k-means, the distance on which k-means depends, it make the clusters into this way. So which is not right. I mean, it maybe look right in terms of practical, in terms of pure mathematics or theoretical, this may look like, but this is what we want to capture. This is one kind of uh, maybe one kind of another solar system. This is another solar system that we wanted to capture. So I mean, you can study, there exist algorithms which are specifically, or not specifically, but designed to handle these scenarios also. So one such kind of algorithm is DV scan, extensively used in astronomy. So when they want to capture the images and want to find the different patterns onto the star, so DV scan algorithm is used. So k-means cannot be used there. But having said that, k-means is very good algorithm. Works very with charm in the practical scenarios. Only thing which we need to know is sensitivity setting to k. So let's answer this question. First thing, first knowledge of how many k to be chosen came from domain understanding. So for example, when we were working on this data of back of the retail, we wanted to create one marketing campaign, and we decided that we want to cater just three kind of customers: good, bad, or average. So here the thing is pretty much clear by the business that my whole customer base should be segregated into these three clusters. Then I will go with k equals to 3. This is pretty much understandable. Now, but thing is that this comes from domain. But as of now, suppose I do not have domain understanding, or maybe I do not get any such requirement or information from business, then I need to find the k. So can anybody think any idea that how can we decide that let's go with k equals to 2, 3, 4, etc. 5? So any vague idea will also help if one can think that, okay, any experiment one can do that, let's go with k equals to 2, 3, 4, 5. Okay, so let's do this. So initially in this scenario, what happened when we do k equals to k means, initially we started with k equals to 2. So this is an experiment when we train the model, when we try to fit the model, we choose k equals to 2. So what will happen? All the data points, say row 1 to row 1000, will divide it into two clusters. Say this one, C1, C2. Now, if I am choosing k equals to 3, I would be having three clusters, right? Now, one very research way of doing is that now you got data points here. What you will do, you will calculate the sum of squared error of all the points to the centroid, right? Here also centroid, Sum of squared error you have already seen. Point minus centroid chi-square, that is it. And for all the points. Now you can assume if there are two centroids, but my data was supposed to be in three centroids, ideal case, let me develop the data. This is one set data point, a small island here, and one other data points, right? To us, visually this is three centroid, but we initially checked with k equals to 2. So what k equals to 2 will do? It will group uh, it will group these data points into one cluster and this into second cluster. Somewhere the centroid will lie here, mean of all the points. Here the centroid will lie perfectly in the center. Now you see, since these points are far from the center, some of the points are far from center, the sum of squared errors of this thing, these points overall would be more than if you would have bring them into island and here into three clusters, right? Because here in this scenario the centroid is far from the points which was supposed to come into the another cluster, so इनके बीच का distance बहुत ज़्यादा हो गया, therefore squared error of sum उनका distance ज़्यादा हो गया, the sum of squared error becomes higher. So point says that for you will create a matrix. Here you will on the x-axis you will do k equals to 2, k equals to 3, k equals to 4. Here sum of squared errors of all clusters, and then the point the k which gives me lesser sum of the squared error, that's my answer. Because the cluster more they are cohesive, jitna I mean if you plainly say in Hindi that jitna wo aapas mein close honge, centroid will lie exactly in between of them. Therefore centroid से points का distance का square कम होगा as compared to अगर दो cluster, the cluster this cluster and this cluster grouped into here, इनका centroid दूर होगा for most of the points. Therefore sum of squared errors भी ज्यादा होगी, और sum of squared error eventually क्योंकि हमारे points तो same ही है R1 to R1000, therefore sum of squared error ऐसा नहीं है कि उसमें ज्यादा points आ रहे हैं उसमें कम points आ रहे हैं, we are just clustering these 1000 rows, that's it. Therefore sum of squared error lesser means I need to choose that k. That's practical way of or developers way of doing finding the k, right? So is that point clear to everyone, or I can repeat it if required?
So, one question, Raj. So,
Yeah.
when you are saying sum of squared error, so let's say if I am having three clusters, so I have to combine sum of square for all the three clusters, correct?
Cluster 1, cluster 2, cluster 3.
Sum, yeah,
Yeah,
for
yeah,
sum
yeah.
of the all three
Oh,
clusters.
yes, and when we have two clusters, then sum of these two clusters.
Two.
So we have two cases, right? Case 1, k equals to 2. Case 2, k equals to 3. Yeah.
And I need to go on doing iterations, and once that is like getting flat, that time I can start.
So the k which gives I mean k equals to 2, 3, 4. The k which gives us lower sum of squared error, I can choose that. So what eventually happen in this case, if you go with lesser clusters with compared to optimal cluster, or if you go higher than the optimal cluster, in both the cases your sum of squared error will start increasing. So this thing somewhat like this way. I mean, finally we need to choose the one for which for which my error is lesser. ठीक है, तो अगेन एक बार मैं ट्राई करता हूँ उसको समझाने का. पॉइंट ऑप्शन, change color, green. Okay, so this is the first case. Here I know that I use k equals to 3, which is the optimal one, so it segregates very neatly these three clusters, right? So inka center of centroid will lie here, practically in the center. Therefore now we calculate the sum of squared error, means all the points इससे distance, simple, sum of squared errors. The formula is point I minus centroid j by square, and we do it for all the points, and we do it for all the clusters. So this is for points I equals to 1 to n, and this is for clusters j equals to 1 to j equals to 3. तो basically कुछ नहीं, इन सब पॉइंट, इन सारे पॉइंट्स का स्क्वायर्ड एरर, इनका स्क्वायर्ड एरर, इनका स्क्वायर्ड एरर और सम, that is it. So that पीछे वाला summation is representing that thing. Now suppose this comes out to be 100. Now even you can understand, in this case, if I would have make them one cluster, this is not there, this is not there, the cluster would be lying somewhere here, maybe here. And you see this cluster, this centroid is very far from these points as compared to this cluster, this centroid. Therefore, these distances and the squared, the squared is bound to be very large. Therefore, the sum of squared of error when k equals to 2 is bound to be very large. And that's why we see that k equals to 2 is not optimal. We go with k equals to 3. Then we try with k equals to 4. If k equals to 4 is lesser than k equals to 3, we can choose k equals to 4. But that if no, that error gonna be again high. Therefore, we choose the one where the sum of squared error is lesser. Right? This is practical way of doing it. Right? First is domain way. Second was practical way. And third case also lies, which ideally is not suitable here. But what we generally can do, maybe I will not suggest you to go in that way. I group my data into clusters. But anyway, that is not the right way, so we'll not discuss. I mean that is the way was used to happen earlier, but people discarded it because it was bad. So stick with just two things: domain. Second is the research way, which is the sum of squared errors, and this is technically the very finest way of finding the best case, optimal k. Right. So eventually, what happened? You would be plotting squared errors. Here the case. The square errors initially would be very high, and it will start decreasing, it will start decreasing, k equals to 2, k equals to 3. Suppose k equals to 4 is the optimal one, you will get the lowest error. Then after that, k equals to 5, it might be flat, and then you choose k equals to 4. It might increase, you never know, but k equals to 4 we will choose, because this point, the almost the error becomes flattened. So this point is also known as elbow point. It looks like a elbow bend. So choose with this day, but purely calculate the sum of square errors here, right? So that's how you can set k n. And finally, it's just experiment of this way. So if domain knowledge is there, plus this knowledge will give you the best case, right? And I think this part is very important, and it is very much understandable, sensitive to outlier, because there are some outliers. If you forget to remove this outlier from initially processing, then your clusters will be very much biased toward basically the centroid. This guy's centroid would be very much biased because it's just practically it's just the mean. So this number is very huge. So that's not good thing. So here EDA means exploratory data analysis. Pre-processing very much required. You need to normalize your data. Why? Suppose column 1, column 2, this column 1 is in the range of 10 raised to power 4, 2 into 10 raised to power 4, but column 2 is just 0.25, 0.26. Eventually you are calculating distances. We will show how distance is calculated for such data. So C2 effect would be neglected because of C1. Therefore, you need to normalize the data. You need to remove the outliers. Third, categorical data. You cannot use it directly. You have to convert it into the numerical data, the way we understand about 0, 1, 1 in the initial cases. But yeah, so this is what a k means. Now try to understand here. Image is given to you. This is the original images, and we have to again segment this data. So ideally you just choose 2k, right? But you can just looking at the images, you can see they are different pixels. Pixels is the form of RGB, red, green, blue. between 0 to 255. So, but you definitely can see this is more than 2 clusters. This color is orange, red, black. So 3 clusters we can straight away see. 4th cluster, green color. 5th color, blue color is the 5th, 6th cluster, right? But I just choose k equals to 2. So now your model will try to fit your data, which is the image pixels, into just two centroids, towards 2 centroid. So eventually he come up with just 2 color. You can see just 2 color here, the orange guy and this blue guy. Now similarly for here, everything into black and peach color. Let's increase k equals to 3. K equals to 3. We started seeing now 3 clusters. One, same shade. This is same shade. This is blue and black shade only. This brown shade. 2 and third. 3 clusters only. Right here, 3 clusters. This one, and this one. And cluster, which I mean to say, is the color. K equals to 4. The fourth and then finally this is k equals to 10. So most of the thing is captured, but still, again, now here you can understand this is somewhere a drawback limitation of the cluster segmentation. Why the computer vision based or image processing was the better way, because even with the k equals to 10 you are not able to predict, but computer vision solves this problem very easily. So anyway, but I understand, you must have understand the idea that with lesser k you are not able to, you just divide it into 3 clusters, 2 clusters. Here k equals to 10 clusters. Yeah. Now consider another problem with the k-means. How you can segregate or group this data. I choose 2 centroids. I mean, this is how my data looks like. And again, this data is mostly toward the astronomy. I'm seeing one constellation, one group of star here. I'm seeing one group of stars somewhere in the same diameter distance here. Now you need to cluster them. You apply 2 centroid. Okay, I can see these are 2. I apply 2 centroid. You choose one data point here, this one, and one data point here. So eventually what happened? All the points, this becomes one cluster. Eventually, if we do k-means, and this becomes second cluster. So this is not right. So this is some kind of limitation of k-means, that it cannot solve this problem. DBSCAN can solve this problem very easily, but we are not studying DBSCAN. Is there any way we can solve this problem with k-means only? So idea is that you understand. I mean, we have seen suppose this is our data and this is some vector y vector. In 2D, y vector is, so suppose this is y vector. So if you project this vector here, so this part will become y cos theta. This we have basic trigonometry, and this part will become y sin theta. So it is possible to convert your features, your point, into some other axis. So we generally have seen x equals to 0, y equals to 0, 2 lines in 2D. These are known as basis vectors. This is a very good point. Why it is known as basis vector? Because all the points, all the 2D vector means this point, suppose 10, 5, can be written with the help of these 2 vectors. So therefore, universally, all the vectors can be written in any direction by the help of these 2. Therefore, they are known as basis vectors. But in universe, there exists infinite basis vectors, right? So if somehow we converted these points is in the 2D space, where x equals to 0, y equals to 0. If somehow we converted them into some different basis vector, x dash, y dash, which is now x dash is not 0, is something else. So can we segregate? So if you convert them from 2D xy notation to some other basis vector, these points will also changed. And if these points are changed, now we can see that there are clear demarcation between them. So we can group them together. So here, this is the use of trigonometry. Here, we change the representation of the data. Suppose initially my data was used to represent, my x vector was used to represent 10, 2, 5. This was with respect to x y, z, which is pretty much we are very much used to. But there exists different basis vector. If you converted them, these points into that basis vector, these points will change the design. I mean the notation, they would change. So this is the second idea. Can we find such vectors, such basis vector in which the points will change its placement. So this is changing the future. So you can come up with some future. So here, what they did very simple thing. I mean, you see, I mean, you very much. I mean, this is very good example. These points almost lies with some radius r. These points almost lies with some radius r dash. So here, shall we make r dash as this axis? This is the second way we are explaining, and these points, all this there's scientific notification of writing a circles with the help of r and theta, another parameter. That parameter becomes our, so r they took on the y-axis, radius, and the theta. So if you do that, these points would be segregated from the red points. No? These are almost with the same radius, and these are almost with the same radius here. You know how converting them from x, y coordinate system to radius theta coordinate system, we converted the representation of points. Now they can be, now you can choose, you know, this one, do the process, cluster here, and finally we end up with the convergence, right? So any point, any understanding of this? Any question till now?
Yeah.
Yeah.
I have many questions. Like,
Yeah, please.
sorry. So, examples what you are explaining, even at the beginning, for the K cluster classification. So, it means that there are, because you are mentioning only in terms of x and y, right? Like on the x-axis and then the y-axis. So it means that there are only two like variables. Is it what we have to understand? Like in the original example.
Yeah, I started with 2. Now eventually we want to see that how this happens with, say, 10 features. Salary, I mean, the way we did in the logistic regression, we have x1,
yeah,
x2,
okay. So
x3, x4.
So it means that k equal to 2 means it is like 2 features, but
no. K equals to 2 is 2 centers.
2 centers, sorry.
Two assumptions of 2 clusters. Now, this data point, so this data point here, this guy belongs to r raised to n. I mean n features. So this guy is nothing but a vector of x1, x2, x3, x4. Now, yeah, but we just maximum we can represent 3, but these all points are nothing. So this point is maybe a guy who is a discount seeker, right? I'm just taking the example of that category. So this guy, or for example, this guy is a defaulter. So this guy feature would be again, for example, number of defaults 10 times, number of time, number salary, etc. You know. So every yes. So every person has its characteristics.
Okay.
Now question arises, which is the next slide. Eventually, 2 points mein to we can find distance easily. I mean, this is the point. This is the point. This looks to me 2,5. This looks to me 5,3 for example. So equilibrium distance हम निकाल सकते हैं यहाँ पे, which is nothing 2 minus 5 का square plus 5 minus 3 का square and square root. So eventually हमें इसके बीच का distance मिल जाएगा.
इसके मिल जाएगा, yes.
Yeah, but now we are dealing with x1, x2, x3, x4 up to xn. Second row is also x1, x2, x3. I mean, these are values up to xn. इनके बीच का distance निकालना है. Therefore, we wanna come up now. How? So first question understood. Second, any other question? Yeah.
Yes. Yeah. The other question is, can you go to the next slides where you converted?
Okay. This one?
Yeah, this one. Yes. So here in a Cartesian coordinate like x and y, you are converting that into like a polar coordinate system.
Yeah, polar coordinate is the right term. Yeah.
Yeah. So, but again, it is just still the frame of reference, right? It is not, for example, we are just only trying to shift or view it from a different perspective and then trying to create the segmentation. But when we go back to the Cartesian coordinate,
you convert
I'm
it
not.
later. Yeah. So see here, this is the frame of reference here is the XY, the Cartesian coordinates, right? Eventually,
Yes.
our goal is to somehow let the system knows that these blue points are belongs to one category. So once I figured
Okay.
out, I mean, once I figured out that these all cases are belongs to C1 or say solar system 1, these points belong to solar
Okay.
system 2. So eventually apply here. These are solar system 1, solar system 1, solar system 1, right?
Okay. Okay.
So after one this is done, there are different ways of visualize them. I mean, it's okay. Initially, just to find them. I mean, if that's the case. So
Okay.
we
Okay. Like
converted
we
into
will
the
go back to the original frame of reference, and
later.
then we
Yeah,
just classify them. Okay.
yeah.
Okay.
Because then we converted from polar to Cartesian back in general.
Okay.
Because or we keep somewhere the mapping that this point belongs to this point,
Belongs
right?
to that.
Yeah.
Okay.
So here you Cartesian to polar. Another thing which I suggested earlier, changing the basis vector. So one basis vector is x equals to 0, y equals to 0. But if you search the net, there are other basis vector exist. We can convert all the points into that basis vector and see if the grouping can be done, the clustering can be done, right? So this is one example. But
Raj?
again, yeah.
No, please continue. I have an additional question. I'll
Yeah.
come
So
again.
but here this is one thing, but when if you gonna go study this algorithm later, and I would suggest go with the DV scan and see how this thing works, and you would be amazed that how beautifully this algorithm works to find such clusters, right? Yeah. So yes, now please, you can answer the question.
My question is, when we are
Right.
converting it into R and theta, usually theta will vary from 0 to 360, right? So this should have been started from maybe the 0 point and then gone on to 360. Why it is divided equally on the right and left hand side of the y or the R axis here?
So again, this is an image taken. You can make the changes if there are some issue in that. The point is that, I mean, if these points and these 2 points almost sharing the same thetas here in the x-axis. I mean, if you eliminate that, but the radius is different. So these points somewhere with the same theta with different radius, they're gonna come differently. So
Yeah,
here
but
the points
at
which are here, right?
intersection, at the intersection theta will be 0, right?
Intersection theta of whom?
No, in this particular plot, at the intersection of R and theta line, the theta will be 0, right?
Here the theta.
Yeah.
No, here the theta is not 0. Theta is this point.
No, Pratik. I think what we have to understand is when we convert into polar coordinates like in R and theta, so you can just imagine that we are looking at in different frame of reference. So maybe the picture is not.
But so what I
it will be
understand
like
is
minus 360 to 360.
any point in as you drawn earlier, Raj, any point in x and y coordinate can be represented as r sine theta or r cos theta, whatever. But theta is basically its angle from x-axis, right?
Angle from x-axis, but
so
just there's one confusion. That theta is just with respect to only on the xy coordinate. So do not consider this theta with the polar coordinate theta here, or because once you change the coordinate, take this point, these 2 points which are lying with the same thetas, for example here, and these point, for example, they on the polar coordinate here in this Cartesian, they are on the different x and y. But if you convert into r and theta, they are having different radius, which is pretty much visual. They are belonging to the radius of this circle. And but they share the same theta. So if you convert that point here, so for example, these points are here and these points are here, for example. So they are having different theta. This is R2. Sorry, this is R1. However, they are having the same thetas. So keeping the same theta but different radius, you create a boundary. So isn't it clear? So with same
Yeah,
theta.
that's clear. But
Then.
But that's what I'm trying to understand. Maybe I'm just because the now since we are considering this theta to be radial, right? So it will vary from 0 to 360 max. After 360, it will again repeat and um, lie between 0 to 360 angle always, right? If you go to the previous.
Mm-hmm.
So when we are converting any point into r theta plane, the theta will go from 0 to 360 always. So that's what I'm trying to understand in this plot here.
Acha, I mean, yeah. So again,
you can consider it as negative and
because,
clockwise and clockwise.
Because if you see 90 degrees also 90 degrees also kind of anti-clockwise 270 degree.
Yeah.
So you can take this way, but eventually that points to maybe if you make this practically correct, I can remove these points which are going toward, and make it into 0 to 360. But if you just want to keep it in minus theta to theta, minus 360 to 360. So 90 is same as 270, clockwise, anti-clockwise. So you can take in this direction as well. But maybe, yeah. So this is little this graph points, data points are little maybe confusing, but idea should be clear that it's just theta.
Yeah.
Between 0 to 360 degree, of course, and radius being the second separator.
Yeah, understood.
Yeah. Okay. Perfect. Anyway, any other question?
So you're mentioning about DB scan, right? So is it like the density based scanning?
Yeah, that one, density based.
Okay. We came across the last.
Yeah. Okay. So this is good algorithm. Another is EM scan, EM algorithm. But anyway, but our in general structured data which we generally see in the manufacturing plants anywhere in the not so specific like astronomy, k-means and then agglomerative clustering is pretty much advanced of k-means, which we're gonna see that. Okay, so before taking a break, Euclidean distance, we gonna just discuss three here, precisely these two, or in fact precisely Euclidean. 2 points here, two points, for example, this point and this vector, we can this point we can calculate the distance, just x1 minus x1 dash ka square plus y1 minus y2 ka square y2. Equivalent distance for n points also work like that way. So we have a row 1, the future of one guy, in which the value is x1 x2 up to xn. The value of here is x again x11 x21 x22. Simple equivalent distance would be same, x1 minus 1, this point minus 1 ka square, so x1 minus y1 ka square, suppose this is y1 y2 y3 plus x2 minus y2 ka square, and all the way to the last column value xn minus yn ka square and summation, the thing which is mentioned here, plain the way we do for 2D. Now the point which I wanted to mention, suppose this point x1 guy is 10 raised to power 5, 10 raised to power 4 in general, the values. So 10 raised to power 4 minus this guy is also somewhere here, suppose 15,000. Another, this is second row, 10,000 per square. But these column, the column C2 value lies in 0.25 minus say 0.03. So you understand that this number is very small as compared to this number, in fact negligible. So eventually what happened, we lost the information which was coming by the closeness of these 2 points. Therefore it suggests to normalize all the columns. So if column row 1 has data 10,000, C1 C2 C3, just 3 points, a row 1 10,000 5 0.25, row 2 is say 12,000 4 0.67. So before calculating the equivalent distance, which is 10,000 minus 12,000 square plus 5 minus 4 square and so on, normalize this column. So all the columns would be normalized. So eventually they will come under the same scale or range. So once you normalize, you remove the effect of this column value being into 10 raised to power 4 or 12 raised to power 4. 10:5, right? Therefore, it is required to normalize the data before running the any clustering algorithm. So coming to the distance, in general, in most of the cases, you're gonna see same distance formula, the same Euclidean distance which we have seen from the school college time. Another distance which is very much important or useful is the Manhattan distance. Manhattan distance is nothing but the absolute. And just one example I want to give you here. Suppose you are going, you are in maze. I mean, maybe you are in the checker box somewhere. Just a moment. These are the points. These are the points here. You want to reach from here to here, right? Now only movement is allowed. Either go to the left, I mean go to horizontally or vertically, right? So you cannot go to this way. So either you can move this direction, this direction, this direction, this direction, this direction, right? So when you are moving, when the distance factor depends on such movement, you go with the Manhattan distance, because right now you cannot move from here to here. You have to move in horizontal or vertical direction, which is nothing but the absolute movement from here to here, plane. That is it. So such kind of movement or distances which is need to be calculated this way, you go with the Manhattan distance, right? So this is nothing but the absolute distance. You can see, I mean, this is absolute and then squared then absolute Euclidean distance, Manhattan distance, just absolute sum. यहाँ से यहाँ जाना है, movement 1, movement 2, movement 3, movement 4, movement 5, 5 distance, right? 1, 2, 3, 4, 5 distance. 1, 2, 3, 4, 5 distance. So all the distances are fine. We can choose the minimum one. So just an idea. So this is how a Manhattan distance says when you want to move in vertical or horizontal bar. So after so this we see later when to use Manhattan distance. But in most of the cases, Manhattan distance is not suitable. For example, if you're comparing two customer profile, customer 1, customer 2. So here you cannot just calculate the Manhattan distance. So therefore, the Euclidean distance always works. In most of the cases, we go with Euclidean distances, but Manhattan distance also comes helpful. Another is the weighted Euclidean distance, generally not used in K-means, but just mentioned here because sometimes we want to weightage one column more. That if as a domain knowledge, I know that this column is very much important for me, I can give that guy a weightage, maybe 0.75. This is not important. 0.20. This is absolutely not important or very rare, seldom important. 0.05 over. So इनका बीच का distance
So
जिसका
Raj,
क्रम है.
maybe sorry, one question
Yeah.
here. So if to find outlier, maybe we can set this weight, right? If say let's say we know our values will range from, for example, 0 to 100, and if something is coming like 105, 110, then we can set its weightage to, let's say, 0 or very low, so it will be removed. Is that understanding correct?
If you know, but I mean, this is some kind of way maybe we try to force to go that way, but again that's not foolproof. I mean, foolproof plan. You should go with the removal of outliers or outlier limitation. So you are saying that I know if this column has one outlier or this column has one outlier, I will give them a lesser weightage. But basically what happens, just because of one data point, you penalize the whole column, which is not right. This column could be very important for me, but it contains outlier. So therefore giving lesser weightage because of that reason is not a good idea. Idea is that first thing first, remove the outlier, or second thing, if not removing, suppose this value is 10, 20, 30, outlier is 1000, for example. If I don't want to remove the outlier, what I'll do, I'll replace the value of this with mean plus thrice standard deviation, which is basically the extreme point of the normal values. So usko limit kar do. I mean, curtail down the value to the mean plus 2 standard deviation or 3 standard deviation. Or you remember the box plot thing, the IQR thing, IQR plus 1.5, these values. So this is known as clipping. Clipping means उस outlier की value को remove कर दो. If 1000, cut it and put it mean plus 2 standard deviation. So this is better way. So just reducing the weightage because of one outlier or multiple outliers, that's not right. The thing is that I know preemptively, I mean, again, this is domain knowledge. I cannot make up something here right now. If I know being provided by the domain that this column has a large effect on the cluster, in that case, I may go with the weightage of W1, but in general, K means all the weightages are equal. So it means 1, 1, 1. So we need to have some solid domain understanding before applying this distance that I should give more weightage. But just to mention here, we mentioned that there exists a weighted Euclidean distance, right? That's the idea. But I think you should at least understand that why just because of outlier giving the lesser weightage is not a good idea, because outlier is just a one row. Outlier is not the characteristic of whole column. The column 10, 20, 30, outlier is not the representative of this column. This may be a value coming by human error. 100 लिखना था उसको, by mistakenly that guy put 1000. That doesn't make this column bad, right? Therefore, lesser weightage to whole column is not a good idea. And also, since this weightage is for all the rows, so your weight will not change for the row in which we get the 1000. No, right? Once you fix the Euclidean distance, you fix it. You fix the weight, you fixed it. That gonna apply for all the rows. Else, your model would be biased that you are putting different weights for different rows. But anyway, the thing which is important is that it's just plain simple. The normal Euclidean distance works the same way Euclidean works for the vector. It's just the vector, vector x1, vector x1 bar, x2 bar, just plain normal vectors x1 bar minus x2 bar square and absolute. That is it. Okay, guys. So this ends the k-means algorithm. So summary, what is important was here the how the convergence works. We see from assigning random initialized cluster to movement of all the data points to the closest cluster, updating the centroid, and finally doing this convergence till it converges. And then we understand how to set k. Best part is SSE, and then we understand the limitations of k-means. Finally, some distance matrices here, right? And the changes of coordinate systems. That's one way of doing it. If it works, needs to be checked and experimented. If so, this is done. Now comes the second case, which we are gonna discuss after break, the agglomerative clustering. And this is kind of an advanced way of clustering and very detailed and little more what I say, computationally expensive. Okay. So I think we can take a break, and it's 8:46 and 8:46 we meet at 8:55.
Okay.
Okay. Yeah. Thanks everyone. Yeah, let's meet in 10 minutes. Yeah. Okay, let's start. Just a moment.
Not just one point.
Mm-hmm.
Yeah. So, like, you'll have to give us an assignment for 20 marks
Yeah,
to
yeah.
complete this, right?
Mm-hmm. I
Yeah.
discussed with Snehal, ma'am. So basically, assignment would be same for the assignment in terms of machine learning, linear regression. I would be sharing the boilerplate code, and then you can just create it, complete it, do the evaluation, and share that with me. So, is there any tentative date in by the time I should give the assignment?
Yeah. So typically before the end semester, we should complete the assignment so that all the 100
Yeah,
marks
yeah,
can be appreciated. But
yeah.
what I request is, like, in the next maybe couple of weeks or within 3-4 weeks, if we before the exam starts, so that we can complete the assignment, then we can be free for studying for the final exams.
Of course, of course. So, yeah, eventually I'll share the experiment or the notebooks with you this weekend, and then you just keep it for 2 to 3 weeks at least, and then you can keep doing in your free time. Or
Yeah.
if you
Okay.
find any issue, you can share with me in our class.
Yes. Sure.
Yeah.
Yeah.
Mhm. Okay. Perfect. Yeah. So I'll do that for sure. Yeah. So algorithmic clustering. Share my screen again. Okay. So we have seen k-means clustering. That's the initial or the very simple or way. The second is the agglomerative clustering, also known as hierarchical clustering. So before going that, agglomerative clustering works in the manner of top to down and bottom to up. So I'll just share you something here before going these too many texts here. Just a moment. Pen. Okay. So in general, hierarchical clustering is the another name of the agglomerative clustering. What it suggests, suppose we have R1 to R2 data points, rows are thousands. So hierarchical clustering, we assume that all our points, so suppose these are points, each point is a kind of a vector of say 10 features, for example. One set of points, this is another set of points somewhere here. So initially the base of this clustering is that each point, each point here in itself is a cluster. So there is no k3, k4. Initially, first line of the code, each point is a cluster. This is cluster 1, cluster 2, cluster 3, cluster 4. Now what we will do, we will merge cluster 1 to cluster X based on the proximity. So any cluster which is closer to C1, that becomes its cluster part 2. So here 1 and 2, these are closer. So these are merged. So let's take this point here. Now try to understand. Initially, forget about all this. Forget this. All the squares. P1, P2, P3, P4, P5, P4. We have just 5 points. First step, all the points are an individual cluster in itself. So 5 points, 5 clusters. Now what we will do, we will calculate which points are closer to each other. So P1 is closer to P2. It's pretty much, we calculate distance P1 to P3 far. P1, P2 closer to each other. We see P5, P4 closer to each other. Basically, out of all the points, we run a loop. We calculate the distance among them, normal Euclidean distance, and we found the one which are closer, merge them. So here we find the least distance exists between P1, P2, P5, P4. We merge them, right? So P1, P2 becomes your first cluster here. Not cluster, I mean a group, right? And then centroid of these points somewhere lies here. Then we calculate, and P5 becomes second group, P5 P4. So now we are somewhere at this stage. We have P1 P2 ka group. We have P3 still individual, P4 P5 ka group somewhere here. Now between this centroid P3
And between center of these points, we calculate the nearest point, again Euclidean distance. And we found that center of P1, P2 is closer to P3. So इनके group को we name it P3. So you can see we are moving up P3, we name it group 3. Again, finally, P5, P2, second point, nothing left. This circle and this circle together becomes one bigger circle. And we name it 4. So eventually what happened? First thing first, the hierarchy, how the hierarchy work comes. We created a hierarchy from bottom to up. From bottom to up, we created hierarchy. If now the graph which is generated on your right side, first thing, this is known as dendrograms. These lines are known as dendro and the graph is known as dendrogram. And now once you created a dendrogram, you have the privilege to cut at any point. Suppose if you cut it here, here you have received two groups, 1, 2 and here 3. If I cut it here, sorry, I have received just two groups, 1 and 2, and 3 is separate and P3 is individual. So basically 1. So this is one point of cutting. Let's cut it here. If you do that, you are basically just dealing with all the points as a separate cluster. This is not what we want. Suppose if we cut it here at this point, now we got one group, cluster 1, cluster 2, cluster 3, right? If we cut it here, somewhere here, we get one group which is combination of this P1, P2, P3, and second group which is just P4, P5. So you know, I mean, you can see that how basically we have created all the hierarchy from bottom to up. Now based on our understanding, we can see how many at one point we can cut. So this is a dendrogram basically. So the point simply lies that here we never design clusters by fixing the k equals to 3, k equals to 4. We create a whole hierarchy from bottom to up, from merging all the points preemptively, so is the right word, and then finally taking the call that at what point should we cut the dendrogram. And then based on the, for example, here I can see my group is now into my, for example, I can see that all these points are belonging to one group. P3 is a one group and P4, P5 is a one group. Then after that, I can calculate the SSE. Simple, same concept which we have studied. For example, if I cut it here, I see now P1, P2, P3 belongs to group 3. The group 3 is somewhat here, this bigger wala circle, and P4, P5 is this group. I can calculate the SSE and then find, shall I go with this? So once you create the dendrogram, there is a function which allows you to cut. I mean, at what hierarchy you want to cut. This is the lowest hierarchy, level 1 hierarchy, level 2 hierarchy, level 3, and so forth. Finally, if you see I cut it here, that doesn't solve a problem because you are basically grouping into all. So not a good case, but the graph we created dendrogram always from bottom to up. And then we calculate it, we cut it from different level and we calculate the SSE. The SSE which gives me the least error, that's the one I choose. Also the domain knowledge. For example, if again assuming P1, P2 are not the points but the some clusters, I see out of 1000 points, 100 points are here, 50, 60, 80 points are here. Only one couple of points, 3 to 4 points were here, 70 points were here, 90, 70 were here. Then if 3 to 4 points are lying here, then this give me some kind of a feel that something is wrong with here, this group. Either this group is very far, some kind of outlier, or this group is not being taken care of perfectly. So maybe these 3 to 4 could be a part of P1, P2 group. So I cut it not here, I'll cut it here. And these becomes a part of here. But again, we need to calculate the SSE. So this is how we create a dendrogram going up from bottom to up, and functions remain simple. Make all the points, chosen points, row point 1, point 2 up to 1000 rows. calculate the equilibrium distance among all the points, and group the one which are the most closer. So here 0.1, 0.2 are the most closer, for example, 0.3, 0.4, 0.5, and always remain B group in terms of 2. Always two points at a time, right? For example, if they are 100 points, we calculate the equilibrium distance of 100 C2. So 100 C2 means almost 2 into 50, 0, 5, 945, 450. This many distances we calculate, and we group the points which are closer to each other. So one becomes closer to 2, maybe. For example, row 1 comes row 10, row 20 comes with row 100, row 200 comes with row 300. This way we group into 2 first. So first dendrogram, first label on dendrogram from bottom will give you the group of 2, and then we calculate the centroid of this group, and then we calculate, for example, just a moment here, R3, R4, R5, R6, 7, R8, R9, R10. हमने देखा कि R1, सपोज R1, R2 एक ग्रुप बन गया, R4, R5 एक ग्रुप बन गया, R8, R10 एक ग्रुप बन गया, और फॉर एग्जांपल R6 और R7 एक ग्रुप बन गया. तो जो ग्रुप नहीं बन पाए, अगर उनकी डिस्टेंसेस आपको करीब है तो they will become the group. For example, R3. If no, they will remain as it is, R9. And then the centroid of these points would be again. Now we have this point, this point, this point, and this point. We will go one more level up from here. We calculate the another equilibrium distance of these 2 points, considering these two as 1, and then we group it. So this way we basically keep grouping and keep making the groups. Right. This point comes with the part, one more group, and finally we get a dendrogram in this way. And then it's a cut where we want to cut. We want to cut it here, we want to cut it here, or we want to cut it here. So each cut will give you a different level of group. So in this toy example, this cut is giving you just 2 groups, this group and this group. No? Sorry, this cut is giving me 2 groups, this group, this group, and this group. Cut above 3 here, this becomes 1 group. This tree it becomes another group. So this is how normal hierarchical clustering works. It produces a nested sequence of clusters as a tree, also called dendrogram. So your cluster is nothing but a tree. You choose the level or the depth or the level you want to cut the tree. If you cut it here, so this is cut, this part is cut. So all the tree beneath this cut becomes 1 group. This becomes 1 group. Here this becomes 1 group. So again, this is a toy example, but on a bigger example, you will set different clusters, right? So before any question in this, before going ahead. I assume there must be someone. I mean, again, this is not that straightforward, but idea is very simple. Different points. Treat every point as individual cluster. Go 1 level up. This is, if I consider this is the lowest level. Go 1 level up. Group the points in the pair of 2. The one which are closer to each other. So suppose these points and this point are closer. So that becomes 1 level. This point and this point is closer. That becomes second point. And this is individual here, no grouping here. Now suppose this was named C1, C2. इनका मैं नाम दे देता हूँ C12. इनका नाम दे देता हूँ, sorry, C13 था ये. C2, C4 grouped into one cluster. इनका नाम दे दिया मैंने C24 with the initials as 24. C5 came as it is. Now you got 3 points at this. Now we have reached this level. C13 is closer to C5. If yes, we join them. C24 becomes individual. So this I name it C135. C24 solo, come here. Now finally the final circle, C1354, which is always the end. We never use that. Now this we got this level, we got at this level, this level, this level. At this level, if I decided to cut it here, you see it is cut here, it is cut here. So this data is now traverse. So this point, and this point. So point C1, C2, C1, C3, C5 become one group, group 1, and second cut is here. So see, this tree is going downwards to terminal leaf C2, C4. So C2, C4 becomes second group, group 2, right? So if the tree is cut at this tree, I would be getting these two sets of group. However, if somebody decides to cut the tree here, now you see there are three cut 1, cut 2, cut 3. Eliminate these cuts. So one group will become C1, C3. C1, C3 become group 1. This cut going downward, C2, C2, 4. C2, C4 become group 2. And C5 individual cut becomes group 3. So more deeper you cut, more number of clusters you will get. More higher level you cut from root, lesser the nodes you will cut. Yeah. So this is just understanding of how the hierarchical clustering works. Now then there would be questioning that how to decide that which distance should I choose. Well, initially this is a toy example, but there would be the cases that 50 points come into 50 points come into one cut, right? And another 40 points here, they are belongs to one category. 10 points here belongs to one category. Now what this is going here, not here. What is the definition of closest point between this and this? That we're gonna understand that how should we define closest for clusters with multiple elements. I mean, see, this cluster is 3 point. This cluster is 3 point. What is the definition of closest? I just tell you the concept of centered here, but that is for the understanding. Things is little different. We're gonna see. So before that, any question in the endogram? How I moved from bottom to up?
No,
okay.
not as such.
Okay, so let's go ahead. Okay, see, now this is the cluster. This is the second cluster. I need to, as I mentioned that, okay, cluster 1 में 3 points है, cluster 2 has group 1 has, cluster 2 has 3 points. Now if I, and there exists one more cluster, this guy, 4 points. Now if this is at some level, say level X, I want to go one level up. Now should I join these two guys? Should I join these two guys? What is the right way of doing that? Now comes the actual understanding. So the definition is closest. Now how closest is defined? For this thing, we're gonna understand three concepts. One is the single linkage, this is term, and then is the complete linkage. So what single linkage says that? Single link clustering. Single linkage says that these 2 points, in these 2 points, I choose the point which is any point. I calculate the distance of this point with this, and this. Then I choose the distance of these point and this, and distance of this point, this. I want the pair which is giving me the least distance. So this pair giving me the least distance. Now there is one more here. These guys are somewhere here. And between this and this is giving me the least distance. And between this and this, there exists some distance. For example, now if this is distance 1, distance 2, distance 3. So I assume if distance 1 is lesser than this distance, minimum of all, so I become these guys as one group. So this concept is known as single linkage, where just based on one link, single link clustering, based on the closest one, I choose the minimum distance. Right? This is one idea. So for example, coming to here, I'll tell you the example of closest pair before going to the farthest link. Or let's understand the farthest pair. Farthest pair says that three point, 2 points, 4 points. Among these clusters, calculate the farthest distance available. The points. So here, just be with me. In this cluster, the farthest distance look to me is somewhat this distance. These guys. Okay, distance 1. And the farthest distance between these two is this guy and this guy, Euclidean distance, and farthest distance between these 2 points is these points. Complete linkage says choose the one which has the minimum farthest distance, right? So if again we are choosing the very north and south pole of these points, very farther points, but out of which is the minimum farthest distance. So D1 is the minimum farthest distance. Therefore, I will cluster them as one. Single engagement, what we did, we choose the minimum closest distance. This is single link. In farthest pair, we choose the minimum farthest link, right? And third category, let's not come to this. Now this slide will make you understand that how the grouping will happen. Okay, see, 1, 2, 5, 6, 3, 4, 7, 8. Initially, these are single points. In itself, they exist. So, abhi, when we make first group, the first nearest 2 points or the farthest 2 points, since this becomes one group. So, be here 1, 2, 1, 2 works same, because at edge of now these are the only points. So the closest distance and the farthest distance, they are same because they're just 1 point. So this point, I think everyone will agree. Now I want to see how this come. Here, out of these 4, the closest link lies between 2 to 5. I think we are all okay with that. This is the closest one. Here, these are the closest one. Therefore, we group them, right? Here, farthest link. We will take the point which are farthest. So here, the farthest point are here 1, 6, 1, 8, 5, 7, maybe 1, 3. These are the or 1, 4. These are the farthest distance. But we will choose the one with the minimum farthest distance. Therefore, they become the group. Now you see how the grouping changed. By choosing the single linkage point, we get this point. We get this upper cluster, which consists of 1, 2, 5, 6. Here 3, 4, 7, 8. But choosing the farthest pair, complete link clustering, we got 1, 2, 3, 4, 5, 6, 7, 8. So this is just 2 way of finding the closest distance. Each comes with their some consequences. And in which scenario this is bad or this is better, in which scenario this is bad or better. That we're gonna see. But I think the closest point is understood. When you choose the closest pair, the closest distance 2, 5, we group them into 1. 4, 7 minimum, group them. Find the farthest point distance. Here 1 to 8. Here 1 to 6. Here 1 to 4. Here 6 to 7. 6 to 4. In सब में से minimum farthest distance, which is 1 to 4. Therefore, then group them. Here minimum distance of 6 was with 7. Farthest distance minimum. Group them. Right? 2 points. So that's how you see how the clustering changes just by the definition of closest. So any doubt in this? Okay. So this way.
Hello.
Yeah.
In furthest pair, so let's say like we are having a group like 1 to 2, 5 to 6, 3 to 4, 7 to 8. Then why I'm not saying that furthest distance is 1 to 6 and 3 to 8?
Which one? Which side?
Farthest pair.
Okay, so here in this or
Like
in this, which is the farthest pair? Uh, let's name
so
it
see
C1.
initially, yeah, okay, yeah.
ऐसा
Now
है ना?
we are having 4 groups. Yeah, correct.
Now C1 C2 के बीच में farthest distance is point point
1
one to
to
point
C.
six.
Yeah, correct.
C1
1 to
C
6.
C1 C4 के बीच में 1 to 8 and C2 C3 के बीच में is 1 to 4 and C1 और C4 के बीच में I'm just writing all the cases 1 to 8.
Okay.
C2
Now.
C4 के बीच में 5 to 8 for example, right? Now you tell me which is minimum in these.
1 2 0
The
6.
minimum is either 1 to 4 or 5 to 8,
Yeah.
right?
Yeah.
So for 1, minimum 1 is lying with this point rather than all the points. So therefore they club 1. So minimum farthest distance.
Okay.
Minimum farthest distance is
Mm-hmm.
1 to 4 and 5 to 8.
Mm-hmm.
So 5 to 8.
Okay. So
Therefore,
every time this grouping will happen between two only.
yeah, every time two clusters always moving from bottom to up in agglomerative. So
In two steps it will move up.
yeah, just always group two clusters together. So each hierarchy, each level would be the grouping of two clusters like that, right? And this way we move. So the graph, for example, here you can relate. Everything is here. Then we group them. This point we group them here. Now this cluster P3 becomes another group here. P3, P4, 5, P2. P4 is the final, the whole universe. Now here then we decide the dendrogram where we want to make a cut. Okay, so important part which is very important here is the agglomerative part is the how the thing which people ask that is that how the closest pair and farthest pair point works. Now everything comes there are caveat that every point every kind of links comes with some pros and cons. So one I mean this is very good, but the cons lies with the single link clustering is that drawback might happen that it forms a chain that 1 2 is closer to 5, 6 is closer to somewhere here 7 8. So 7 8 is close, 8 is closer to 9. So you keep on joining this group. Where could be the case that 7 8 instead of 7 8 which is lying somewhere here 3 4 might be a case which should come up into this group, but you lose this information because you are just finding the closest distance here and making the chain. So this is the drawback of single link clustering is that you might form the chain of clusters in only in one aspect, one direction. Farthest pair point is that your cluster may be huge. So here you choose the longest farthest point. Suppose if your data is very sparse, very sparsely located in n dimensions, then just because you are considering the farthest point and minimum distance, your clusters may become very big clusters, which is not good. Eventually, the best part lies that people we will create single link cluster, people go farthest pair cluster and take the best out of that. Third case, people take average of all pairs. Basically, they take the average of all pairs, average of all the small distances, all the farthest distances. But important is that in general, if you go with the default uses, they wanna go with the complete link clustering because they make sure that your clusters do not form chain and all the points remains cohesive. They takes care of that. But again, this is different style of clustering. It's all about just experiment which closest definition helps me. This is similar to using Euclidean distance in k-means. There are Manhattan also, but we cannot use Manhattan in k-means because means always go with the Euclidean distance. In Manhattan, the things if you're gonna go with the Manhattan distance, k-means changes with k medians. Then you calculate medians. But again, that's something else. But yeah, so But overall, the thing which is required to be known here is that, so for example, this thing, calculate the complete linkage models only take care of that. Is just that we need to take care of once the dendrogram is created, we have to decide that which link should we do, all the experiments, all the analysis after that, how many points ended up here, calculating the SSEs, and then finding, okay, if I cut it here, then I'm getting this SSE. If I cut it here, then I'm getting this sum of squared errors. Which cut give me the least sum of squared errors? I choose that, right? This is one thing. If this information plus domain knowledge that I am my problem in general lies with the four groups, then I prefer the cut where the points are lying having 4 groups. Or if I'm seeing some groups are having very less number of data points, then I think that's not the right group. That should be part of the other group. So I cut it accordingly. So these experiments we have to keep doing in the clusterings, right? So yeah. So finally, this is what agglutinative clustering works. Coming to the last slide here. So let's look at one-to-one k-mean here, agglutinative here. First, understanding k-means, benefit of k-means, very much used in the development work. You can quickly solve it in almost negligible time. Fast, scalable, but rigid. Rigid because it assumes our clusters is roughly some kind of circular shape and like that. Agglutinative, flexible. Why flexible? Rigid. Why? It assumes k equals to 3, 4. You make them fixed. K is 3. Now your model is bound to make 3 clusters, even if the cluster has the nature of just having 2. I mean, the data has the nature of just 2 clusters. But when we make it k equals to 3, they are bound to make 3 clusters. So basically, destroying the clusters. Therefore, rigid, flexible. Why? You create the graph totally from bottom up till top, and then you have the full flexibility of cutting it the point where you want. Interpretability, you can at every level you can check, okay, these many data points are here. Now you can visualize this data point. There are techniques which makes you visualize the points in n dimensions. You can assume, okay, these are looking to me same clusters. So some techniques are known as TSNE. Maybe time permits, we will see, in which they convert your n dimensions into 2 dimensions and shows us onto the plot, and we see points, okay, these are the clusters. But at every level in the dendrogram, we can cut it and visualize these points. Are they belonging to the same clusters? So therefore, interpretability. Expensive, you understand, because we are moving upward. We are making too many calculations in each level, also between each cluster, right? So they were too much expensive, this algorithm. But again, happens in very real time, so it's okay. Understanding the aspect. K means partition based. I mean, we make the partitions, we make the hierarchy bottom up. Basic idea was in the k-means was that we assign points to k clusters. We assign 3 points and then minimize the inter-cluster variance, basically sum of squared errors. Here, we assume each point is a cluster and then we move up. We merge cluster in a pair of 2 till we reach to the top. Here, yes, of course, you need to specify the k. In k-means, no. You can decide later using dendrogram. So dendrogram is the very handy tool in this hierarchical clustering. Scalable, very fast, ON. Poor scalable, O raised to ON square. So if our data points increase too much, it will take almost n square. So basically quadratic is the complexity. Fast, slow. Cluster shapes. It assumes my cluster is spherical. Therefore, it failed in the cases where the data was somewhere like that. So it will not work here. Can handle arbitrary shapes just because of the linkage. If I, for example, in this case, if I want to capture this nuisance of the data, so I will go with the single linkage because I want to extend this chain. Instead of this being closer to this, I want to make this group, combine them, one group, this group, combine them. So I want to keep it making links. So this can be achieved with the help of single linkage because I want to bring the chain, keep the chain continue. So therefore, depend on the linkage, you can handle the arbitrary shapes. Distance sensitivity, yes, sensitive to initial centroid, depends on the linkage. Deterministic means you cannot determine initially, because initially you will assign random points as centers. Here, everything is deterministic because we are giving them the distance that choose all the points and go with either single linkage or closed linkage. Complete linkage. Outlier, this cannot handle outlier because we see it means. So any number 10, 20, 10,000, 10,000 will affect the mean, making the centroid push toward the outlier, thus affecting our cluster. This is also sensitive, of course, but somewhat lesser than k-means can be handled with the help of linkage, right? So for example, if my point is very far and this is some point, so instead of then, if this point is far, I can go with the farthest complete linkage because eventually this distance will be minimized and this distance will never come into the picture. We choose minimum farthest distance. So such workaround can be done, but again, both are sensitive. Interpretability moderate. This is highly interpretable because of dendrogram. Memory usage low. Just one time here, these distance metrics because you are doing a lot of computation. Finally, large data sets with clear cluster, you can use this example. If data set is very small, medium data set and involves hierarchy, where you perceive that the nature of data involves some hierarchy, you can go with the clustering. However, both the clustering can work together. So this is something you can have a look later. But understanding is basically the fundamentals needs to be understand of this thing. Yeah, guys, this ends about two kind of algorithm here: k-means and agglomerative. Beside k-means in general, agglomerative, there exists, as I mentioned, DV scan. There exists EM technique, but they are for very complex scenarios. But yeah, so not the scope of this course, but even in the practical scenario, we mostly use k-means and agglomerative. In general, agglomerative we use, but initial checks, POCs, can be done with the help of k-means. When you at least need to find that what are the quick number of clusters, are we still able to segregate our data into some group? So instead of agglomerative, we will go with the k-means with k2, 3, 4, and then we complete the POC. And later at the time of actual production, we generally go with the agglomerative clustering set. So yeah, this ends our clustering. And so any question in this? Of course, you need to have one look again, and then just go through the fundamentals, and then this will start making sense. Yeah, so now over to you guys. We are already over with the time. So anyone have any question?
So Raj, one small request. So these algorithms, whatever we are learning, right, for supervised, unsupervised, and all the different algorithms. So maybe I was just thinking if you can give the assignment in terms of solving some simple questions or some simple problems using different algorithms, so that the algorithms will be handy for us to remember.
So you want in terms of practical coding or in terms of theoretical understanding?
Maybe first thing, like major focus is on theoretical understanding. This is just my personal opinion. What is happening is, like, when I'm trying to recall all these algorithms, so concept when I read it, वो समझ में आ रहा है, but to have it more solid in terms of, let's say, which sort of algorithm should be used, or what kind of algorithm we should select for which kind of problem. So
okay.
if there are some small practical problems which we can solve.
Understood. So okay, I take your point, but just remember two things is here. I mean, first thing first, this is I think pretty much clear to you that when to use supervised, when to use unsupervised, right?
Yes.
Now thing is that even if you do the practice, first thing you need to boil down is that are you solving a regression problem or a classification problem?
Or exactly, yeah.
Now, if you're solving a classification problem, in general, there is no hard fixed rule that you should go with logistic regression or why not you should go with random forest or decision tree, right? So ideally, there is not a case that anyone can tell always go with logistic regression, always go with random forest or decision trees. This thing always will come with the practical. However, the thing which I can not as an assignment, even as some kind of maybe notes which I can provide you under which scenarios these algorithms specifically works well, right? That you can brush up later and use that in your practical. That I can give you a scenario. Okay, for this scenario, random forest is the best one, or works best in the past. You should go with random forest. For example, in universally in all the cases, random forest will work better than decision trees in 100% of the cases. So this is pretty much understand, because random forest has more decision trees. But there are some cases the random forest will not work best, logistic regression might work best. So okay, I'll keep this point, then maybe try to make the assignment in that way. Some kind of notes which you can go and then apply that practically. So yeah.
That is one point, and the second point is in terms of the examples. So I know that, okay, like you're trying to give very simple examples just to understand how the algorithm works, or where should we use that. But maybe like if you can have one exercise, or maybe you can show one example of the EV applications. Like I was reading some papers on some BMS algorithms. Okay, so there they are using some different machine learning algorithms to estimate some battery parameters, like some recursive least square methods, or some feed forward neural network. So there are many, I know that, but in practically, like since you're already in Hella with working on these kind of actual applications, right? So if you can, let's say, give one case study or one.
This I can do. So so BMS and even such kind of data, maybe I try to procure, which is available freely. I can at least show you one full-fledged problem scenario from the real production.
Yes,
exactly. This I'll try to do that, and
Yes.
and of course so eventually I gonna apply only the things which you have learned. For example, linear regression, logistic regression, for example. The feed forwards, these are part of deep learning. Maybe I apply you that, you understand that thing, but again, you need to understand that later, that how this works, neural network works. So feed forward networks are nothing but the artificial neural networks. So yeah,
yes.
I'll keep this point also.
I'm just only trying to make a correlation with whatever we are learning, so that practically all the EV applications, or whatever is related to our domain, if that can be useful, so then we can straightforward.
Okay, got it. Yeah. So this thing we will keep it that way. Maybe one data set from the real world, and then we look at that, we process that, and then apply a machine learning algorithm on top of that. Okay, but yeah, point is that again, easy examples, because with hard examples these points would be very difficult to teach.
Yes, understand. No, totally agree.
Yeah.
Yes.
Okay, so yeah, both points taken. So I'll keep that thing. Okay, guys. Then thanks everyone. Already late. So two things. I will be providing assignment by this week, this weekend, and then you can discuss 3 to 4 weeks, and let's submit it by end of the semester, before end term. So,
yeah. Okay.
Okay then. Thank you everyone. Yeah. See you. Take care. Bye. Bye.